I'm really excited to do this problem with you. Why? Because it's such a fundamental thing. So this problem says, calculate the area of a circle by doing a double integral. Okay? So area is the double integral over the circle of dA. Why am I so excited? Because you are calculating the area of a circle. Okay? So you might say, Paco, what are you talking about? Why is that exciting? The area of a circle we already know is pi r squared. I know that since I was 12 years old or whatever. I don't know when you were taught about the area of a circle. But actually, why is it pi times r squared? Has anyone ever proved it to you? And if not, let's do it now. So, let's pretend we don't know how to do integrals in polar coordinates. So let's do it in rectangular coordinates. So in rectangular coordinates, the area, let's integrate first along x, and then the result we integrate along y. Okay? But what are our limits? So our limits is, if we are integrating along x, as usual we do a line along x, so we enter the circle at this line here, and we exit the circle at this line here. Okay, so we need to find the equations of these two lines. We need to solve for x. So how do you do it? Well, we know that the equation of a circle is x squared plus y squared equals r squared. And therefore, if you solve for x, you get that x equals the plus or minus square root of r squared minus y squared. So it is quite simple to see that this line corresponds to the positive square root of r squared minus y squared, while this line here corresponds to the negative square root of r squared minus y squared. And those will be the two limits, which I will need more space to write them down. So this will be square root, the minus square root of r squared minus y squared, and this will be the positive square root of r squared minus y squared. And then the limits along y, we have to project this circle into the y direction. So when we project it into the y direction, we just have to integrate from minus r to r. So those will be the limits in y. Now, this starts easy, so we can do the inner integral very easily, because it's 1, right? It's the integral of 1, because that's how you calculate areas using a double integral. You choose 1 as the integrand, yeah? So the integrand of 1 is equal to x. But now we need to substitute the square root of r squared minus y squared, and then the minus square root of r squared minus y squared dy. So this will be the integral from minus r to r of twice the square root of r squared minus y squared with respect to y. And this is a relatively ugly integral to solve, okay? It's not impossible, but it's very ugly. So clearly, integrating a circle using rectangular coordinates is not smart. It's clearly better to integrate a circle using polar coordinates. Why is that? Because in polar coordinates, the limits suddenly become really easy. So if you are doing the integral in polar coordinates, so let's say we're integrating first in rho, and then we're integrating in phi. So what are the limits in rho? Well, the trick is you draw a line in the direction of rho, so from rho equals 0 to infinity. And when do you enter there the region of integration? When rho equals 0, so you write a 0 here. And when do you exit the region of integration? When rho equals r, so you write r here. And then you project this area into the phi axis, okay? Or in other words, you project it onto, it's very difficult to picture this, but imagine you project it onto a circle, so you end up with a circle. So the limits on phi are clearly from 0 to 2 pi, right? This is clearly a much better way to calculate the area of a circle. However, we forgot something very important. We forgot to include the Jacobian for dA. Okay, so let's check that. So if we try to calculate this would be integral 0 of 2 pi of rho evaluated between r and 0 d phi, which is equal to integral 0 of 2 pi of r d phi, which is equal to 2 pi r, which is not the area of a circle. So this is wrong. We forgot the Jacobian. Now, I can guarantee you that at some point in your lives, you will forget the Jacobian. Hopefully not in the exam, but every PhD student I have had, at some point during the PhD, we had a meeting. This is not working. I mean, it's something much more complicated. It's an integral in Fourier space. It's not even x and y. It's the wave vectors, whatever. It's completely much more difficult than this. But still, what happened is that they forgot the Jacobian in the integration. Okay, so really important, never forget the Jacobian. So let's not forget the Jacobian. So what is the Jacobian for the polar coordinates? You can get it either by geometrical intuition, like we did, so dA equals rho d rho d phi, or you literally calculate the Jacobian analytically, which we also did, and we, of course, we arrive at the same dA equals rho times d rho times d phi. So therefore, having found the dA is equal to rho times d rho times d phi, now we can calculate the area very easily. So let me get some space. So the area is the double integral of dA, which is the double integral of rho d phi. And now we need to find the limits. So first, the limit of rho goes in the first integral, and then the limit of phi goes in the outer integral. So this will be the integral from 0 to 2 pi. That's the limits in phi. And the limits in rho are from 0 to r. And now we are integrating rho d phi. Now we can actually do separation of variables, separation of integrals, because the integrand is a function of rho multiplied by a function of phi, which is 1, okay? So rho is equal to rho multiplied by 1. So this is a function of rho, and this is a function of phi. So we can split the integral into two. So this will be equal to the integral from 0 to 2 pi with respect to phi of 1, yeah, times the integral from 0 to r of rho with respect to rho. So the first integral of 1 is just phi. We substitute 2 pi, so this is 2 pi, times the integral of rho, that's going to be rho squared over 2, evaluated between r and 0. So that's going to be pi times r squared. The area of a circle. So this is a proof for the area of a circle, just doing an integral in polar coordinates, and it's really, really easy. Thank you very much. See you in the next video.